Good morning, everyone. Welcome to the IDAP 25's third keynote presentation session. This is our second day on 9th International Artificial Intelligence and Data Processing Symposium. I would like to sincerely thank Assistant Professor Mohammed Al-masni on behalf of the IDAP Organization Committee for accepting our invitation to serve as the keynote speaker for IDAP 25. Dr. Masni is also our organization committee member, and he's our keynote speaker from Sejong University side. As you know, this year we are organizing a joint symposium with Sejong University and Incheon University. In 2011, Dr. Al-Masni graduated from Cairo University, and also he received his master's degree from Cairo University. After earning his PhD from Kyunghee University in the Republic of Korea in 2019, he has been employed as an assistant professor at Sejong University, at Sejong University's Department of Artificial Intelligence in Seoul, South Korea. Artificial intelligence, machine learning, deep learning, signal processing, computer-aided diagnosis, and medical image processing and analysis are among his specialties. Dr. Al-Masni has been published more than 90 conference and journal publications. He was one of the distinguished professors in his university around the world. I don't want to take our listeners' time too much, and we will be listening to Dr. Mohammed Al-Masni during his keynote session. Dear Dr. Mohammed Al-Masni, the stage is yours. You can start your presentation. Thanks.
Thank you very much for the kind introduction. And first of all, I would like to thank the organizers of International and Artificial Intelligence Data Processing Symposium for kind invitation to provide this keynote talk. Okay, I am Mohammed Al-Masni, and I'm going today to deliver a talk about AI solutions for data limitations and label noise. And I'm going to focus precisely on brain tumor segmentation in MRI. As Dr. Afan, he introduced me, I'm also leading a METI lab, stands for Medical Imaging Technology and Intelligence at Sejong University. And in our lab, we are actually focusing on these four main research topics, including image segmentation, image-to-image synthesis, and motion artifact correction in MRI, as well as the cross-modality image registration. And today, I'm going to spend around 40 minutes on those contents. And before going in details about the challenges for any AI segmentation tools, especially for MRI technologies, so I'm going to start giving you some intuition about the MRI sequences, which are different images created by MRI scanner. And after that, I'm going to highlight three main challenges, like a missing sequences or noisy available of noisy labels, and as you know, in a medical domain, we are suffering from data scarcity, and how we can address these kind of problems. Okay, of course, I cannot start with this without giving you like a brief history of AI. So maybe, as you know, in the last century at 60s, it was like a first golden age where maybe the first neurons, neurons attached every neuron with the weighted maybe factors. Then maybe in the second age, where multi-perceptron with the multi-neural networks came out with the back propagation technologies. And of course, at the 90s, 80s, the invention of CNN, convolution neural network, came out by Lincoln. But the problem was in the computer limitations. So we don't have a graphic processing unit at that time, so we cannot make those networks deeper and deeper. So maybe in last decade, maybe around 2012 and moving forward so far till now, we can see the third golden age of AI, where now we are talking about the GANs models, transformers, and the language models. And we can now see a lot of language vision models, which can promote a lot of healthcare applications as well as other applications. And we can summarize those technologies as here. Starting, for example, with the CNN, we may have a ResNet and other maybe types of transformer-based vision transformer and SWIN transformer, and going to the language and diffusion models, including that ChatGPT. And maybe the trend nowadays is, of course, if we could have a model that could be generalized for every task, which we can call it as a foundation model. And as Sam here an example. And as you know, we can categorize the tasks based on AI, based on like classification only or classification with the localization. Of course, here, if we have only single objects, what about if we have a multiple objects? Then we can go deeper in object detection or instance segmentation. Those like main categories and tasks can be developed for including AI. But of course, if we are talking about medical image analysis, then we need methods and algorithms that could handle the synthesis or reconstruction techniques, the denoising, especially if there are some artifacts, and the explainable AI, and of course the CLAP, which is a part of language and image models. Okay, now let me start with the first item in my presentation, which is about MRI sequences. So if you are familiar with MRI, that will be just a review for you. But if you are new in that field, I believe that could be like a good initiation for understanding the MRI and other things related to this. So MRI scanner based on different imaging parameters and different imaging sequences, then we can create different data. We call it a sequence. So we have a T1, you can look something like this, or a T2, or a flare. And of course, here with the T1 contrast enhance. As I said, if you change, just alert the pulse sequence, maybe shorten or do a lengthy TR, which is repetition time during the acquisition process, or you do the same at echo time, which is the time that we collect the signals from the patients. Those create those three different actually maps or sequences, T1, T2, and proton density. If we would like to change the pulse sequence, then we can go with the flare. So what is difference now here in these sequences? You can see in the first T1 images that it can, the fat region appears here in this region, it's appeared like bright. And the water, which is a kind of blood in our brain, like this part, CSF part, it becomes and appear as a dark. But if we go to the T2, which is we call it in time of relaxation, because here our data acquisition is based on the time, then T2 relaxation, which is a T2 weighted images here, it's flip the appearance of T1. Okay, so you can see here the inter part, which is that CSF, which include actually a blood, it becomes here a brighter. But the fat region, which is our brain tissue, it becomes a darker. And you can see, please notify the region of the tumor, which is the part that we are focusing to segment at the end. So you can only see small part here of that, but here, this is for the same patient and the same slice in our brain. So here more details came out. And similar thing is for flare. It is actually based on the T2 acquisition, but we alter the, we call it the flip angle from 90 to 180 degree during the scanning. So what's happening here is CSF, this part, we said it is somehow related to T2, right? So it suppresses that CSF part, so it becomes a darker. And the other tissues, it becomes a brighter. Then you can see other details for that tumor. What about this one, T1 contrast enhanced? It's simply it is a T1, but it's maybe formed after injecting a patient with the gadolinium, some contrast material. So some parts, especially for example the enhanced tumor parts, get highlighted. Okay, so here is different maybe characteristics of different tissue with the different images along with a dark or a light appearance. So what's happening now, actually, if we would like to use those kind of sequences in MRI diagnosis, then clinicians actually preferred some of these sequences in a certain tasks. For example, if maybe clinicians would like to measure your tissue maybe volume, especially for gray matter or a white matter, those regions, then they prefer to use a T1. So we can say that T1 is for anatomy. Okay, but if you would like to go with a T2, then that is actually preferred for water fractions computations, especially here, for example, for the edema part, which is a part of brain tumors. And of course, there are a lot of other sequences in MRI, including diffusion weighted imaging and susceptibility weighted imaging. And all of these are specifically for some diseases. So we cannot use, for example, diffusion weighted images to highlight some other diseases, for example, the brain tumor, but it's used for stroke. So it's based on the clinicians know well what's happening in our tissue, then they would like to check the differences in those parts. So now, how we can make AI took those different images and came into different diagnosis tasks, including, for example, segmentation or just a classification, or if we would like to do some image synthesis. So that is our task here. So today I'm going to talk, as I told you, 3 different challenges in the segmentation broadly, and in MRI for brain tumor segmentation more precisely. So the first one is a missing sequences. Now you know what's the meaning of sequence, right? It's MRI sequences. So usually for the task of brain tumor segmentation, we need actually 4 different sequences that I showed to you, which is T1, T2 flare, and T1 contrast enhanced. But the problem actually is not all the healthcare institutes provide those and do the scan for every patient, including those 4 different sequences. And the reason here is the cost and the inconvenience of the patients to be scanned 4 times, for example. So what's happening? It came out with the missing sequences. Then, for example, for certain patient, we have a 1 or a 2 sequences, or 3 at most. Then can we still deliver a good segmentation outcomes using those? So that is the missing problem. So another problem is a noisy labels, which is, you know, that usually we are depending on supervised learning, which means that we need to get the ground truth contours. So what's happening here during the labeling, it is not just an image, then we can say it is normal or abnormal. It is based on the pixel value or pixel location in your in our MRI image. So usually we have some noisy in a labeling, and that actually affects our segmentation paradigm. Another thing is a data scarcity, and this is really happens in a medical domain because not all the people are patients, and not all the people came to the hospital and make scans have those such abnormalities, right? So we have a data scarcity problem, especially for maybe cohorts of pediatric, for example, compared to the adults. Okay, before going into those 3 problems and 3 solutions for them, let me start talking about the problem itself, which is tumors in a brain tumor segmentation. Here is an example. We call the brain tumor as a glioma, and that glioma contain high glioma level and a low glioma level, and actually it contains 3 labels. So we have an edema part, which is the outer part, And we have the necrosis part, which is the deep tissue part here. And we have the enhancing tumor, which is a part between the necrosis and the edema, which is a part like it's still actively growing region. So, and if you looked statistically into the data set, we are talking about 3D volume, not a 2D. This is just a 2D example here. So what's happening is, if you look into the contents of the volume, you can see that 84% of that images are actually background, which is the part here, okay? And 15% actually is the healthy region, which is this part, right? If you can see my cursor here, okay? And only 1% of that volume can contain those three different tumor types. Now you can just get to the point that how it is difficult to get those maybe abnormalities as a 1% of that volume. We would like to detect it and segment it into three different subtumor types: edema and enhancing tumor and necrosis. And actually, this is almost similar maybe when we talk about the high glioma level, high-grade glioma and the low-grade glioma levels. And for the data sets, actually, we are working on PRATS datasets, which stand for PRATS brain tumor segmentation datasets. And that dataset provides us 4 different MRI sequences, like a FLAIR, T1 contrast enhanced, and a T2 and a T1. So you can see that every sequence can highlight a specific portion of that tumor, right? And here is the ground truth containing the 3 levels. So here, an example that show you that the 3 ones with a 3D volume, then we can see like slices, slice by slice. Then you can see the overlaid segmentation, the brain tumor part here. So what's happening is actually we are in need of these 4 different sequences, okay, in terms of providing a good segmentation results. But actually, in real cases, in a real application, if you go to any hospital, then they will say to you, we cannot do all of these imaging for every patient. It takes a lot of time, and at least one of these sequences take around 15 minutes in terms of data acquisition, and it makes it a lot of problem. And based on our practical work here with the collaboration with the Seoul National University Hospital, they prefer actually these 2 sequences in terms of providing a good results. So as a clinical application. So if you look to this, we say that FLAIR is a part of another altered of a sequence plus a pulse sequence of that T2. And a T1 is the same as a T1 here, but including the contrast enhanced mechanism. So actually, we can say that our main problem is that the 4 different MRI sequences, they are not available everywhere. So how we can then do the segmentation using only some of these data. And just to give you intuition about what's happening, if we have those 4 sequences, then we can train any AI segmentation model so that we can perfectly get a good segmentation results of these 3. Then what's happening if one of these sequences are absent? So for example, let's assume that FLAIR1 is absent at this time, and we train the model using only these 3. If you look to the results, you can see that it's totally different. And we cannot get a good results using these 3 sequences. So we'd like to solve this problem, actually. This is a missing sequence problem. The first solution for this is we propose here a knowledge distillation work, and this work was conducted with a collaboration, as I said, with the Seoul National University Hospital as well as the Yonsei University. And we tried actually here to solve the problem of these missing data. And the way to do that is to distill a knowledge from a teacher model that can train using the full knowledge, the full 4 MRI sequences, and distill those knowledge into a student model in a latent and a pixel level spaces. So we'll see the maybe description here. So what's the meaning of teacher-student model? knowledge model, which is a knowledge distillation. Actually, if you have, for example, a data set here, and you can actually, for a training, you can train whatever high-level model that contain a lot of layers, right? It's easy. It's just a training part. So we can actually, your teacher can train using a very maybe heavy networks that include a lot of layers. But actually, in terms of deployment, which is a real-time deployment, we need a faster neural network algorithm. So we can actually select maybe a simple algorithm that contain, which we call it the lighter network. So what's happening is then we can retrain this student model using the same dataset, but besides that, we can distill the knowledge. For example, we can take some latent features from the teacher, and during the computation of a loss, we can consider that. So we can take a feature from here and a teacher features from here, and we can cross computing the loss, as well as using the soft label predictions from the teacher model to the student model. That is the knowledge distillation. And here you can see that the main idea behind this teacher-student model is to transform some maybe heavy knowledge from that teacher model into small student model for the purpose of making it faster, because it is a lighter network. So based on this idea, actually, we come with the our knowledge distillation and network for brain tumor segmentation. So what's happening is, again, we have a same network, just one for as a teacher and another one as a student. So in the teacher, we use the four maybe available sequences: T1, T2, flare, and T1 contrast enhance. So from where we get that? Actually, we get that from our public dataset, because our public dataset contains those four images, four sequences. So we can actually get the benefit of using all of these. But in terms of a teacher, in terms of a student, we only use a specific amount of them. Could be in our study here, we fix it to be 2 or 3. So we have two options. If you have 2 sequences or 3 sequences, then you can get a knowledge from this, from a teacher to students. That is a distilling the knowledge. So how we can distill a knowledge? In this case, actually, we try to do it in a different at a different levels. The easiest one is at what we call deep supervision. So we can take a prediction at 3 different levels: the last outcomes, and the layer before that, and a layer before that. So we have 3 outcomes from a teacher. So we can compute actually the loss between that and the loss. It is something like we are forcing the student model to follow the same thing as a teacher model. And the other thing is based on the latent features. One at the bottleneck, so we can get a feature space here, G1 and a G2 from a teacher and from the students. And then we can compute the correlation between them. And the main purpose, as I said, is to get those maybe attached to each, matching each other, because we know that this is working on a full data information. So we are using here a parallel twins correlation coefficient paradigm, as well as we do that as an impeding from some prediction layers. So we applied some perceptron neural networks to get those embedding features. Then we compute other correlation again. So we have actually different levels of sharing the knowledge or distilling a knowledge from a teacher to students. So during this study, we had performed some maybe different addition to the network. And you can see here, including all of these things, it can increase the results of tumor core, enhancing tumor, wall tumor, different tumor types here from a baseline, which is appear here as dice loss, till what's happening in this location. So at the end, we can now use, for example, only flare and T1 contrast in enhanced image as a testing image. So at the inference time, actually, we need only to test the student model, this part, right? So what's happening is using the Pratt's 2021 data set, we only use the FLAIR and T1 contrast enhanced images, and we compare different models. So if we have, for example, a baseline which is optimized in a unit, or our task, which is a distilled knowledge from that teacher-student model. So including the NN unit and unit R and SIG ResNet. So if you can see here, so we got the highest average DICE score for all the tumor types. And for the clinical application, we used the Seoul National University Hospital data, which, as I said, they provide us only FLAIR and T1 contrast enhanced. Okay, so we do the only the test using all these networks, and at the end we have again the highest performance here again. Okay, another way of thinking to solve this missing sequence is to synthesize the missing ones. Okay, we said we may have a 1 or a 2 or a 3 sequences. Why not? Because we are still using the same brain, right? Can we make like create or develop a neural network that could take those inputs, the available sequences, to synthesize, to reconstruct the missing ones? That is our maybe collaboration from our lab, METI lab, with the Cairo University and a KIST and MIT and Harvard was done, and we published this work here in Alexandria Engineering Journal. So again, the aim here is to address the problem of missing the sequences, and we did that using the synthesizing the missing ones, using the available ones. Then we can do the segmentation using the available ones plus the synthesized one, then we can get the good results. Here is the framework. We can have a data acquisition. For example, we have a certain number of sequences. Then we can check them actually. Let's assume, for example, we have T1, T2, and a T1 contrast enhanced sequences, and FLAIR is the missing sequence. So how we can do that, just to automate the process, we can have a sequence identification model, a simple model based on ResNet that could easily provide us the sequence name. So for example, T1 is available, T2 is available, FLAIR is not available, and so on. Okay, after that, we can check actually about that FLAIR, because our assumption in the beginning is if the FLAIR is missing. So if the FLAIR is missing, then we can do the image synthesis using those available ones. I have a T1, we have a T2, T1 contrast enhanced. We develop a new version of that generative model using a batch again, and then we can get a synthesized version of the FLAIR. Then we can combine these 3 sequences, and then that synthesized FLAIR ones, then we can go to the segmentation model. Now we can train actually our model using those 4 sequences, or just do the inference in this time. Okay, so maybe the main contribution in this work is the idea itself of synthesizing the missing sequences. At the end, we have some innovation here in the GAN model. So what about the models itself? Here is the synthesis as a task, which is it's a GAN-based network. We had attached squeeze attention block at every encoder and every decoder layers. And instead of just having a discriminator to be based on the image, we have making it as based for the batch level, so we can have a good discrimination output here. And I believe everyone now here know about that generative GAN models, which contain 2 models. Generative model, that token input could be our available ones that generate some FLAIR images, and based on the BRATS data, we have the real images. Then we can compare them just using that discriminator, and then get the network updated to reweight the generator networks to fool the discriminator. And for the segmentation task, at the end, we use the optimized NN unit. Just it is a simple unit with a specific maybe 7 encoder and decoder layers, and with a deep supervision, the ones that appear here in the green parts. So now we have 2 results I would like to discuss with you, which is one for the image synthesis and the other one for the segmentation. So what's happening here is, this is 4 different examples. We have just checking that which maybe sequence could be better in terms of providing us the flare. So for example, if we are using a T2 or a T1 or T1 contrast enhanced, so you can see that in terms of image visualization, we are coming with the same flare image. So using those actually, because we are dealing with the same patient, so just now it's an acquisition problem. So we can easily find and create or generate those flare images. But if you go to the maybe some index score using the similarity structure measure, then you can see that using the T2 actually providing us a better results in terms of similarity structure for all these cases. And you can see here we compare our synthesized network with the other one, and you can see that the metrics in terms of using our synthesized for the segmentation is better than the others. And even it is a lighter compared to the others. And for the brain tumor segmentation, here a really interesting results in this table. For example, let me introduce the first thing, which is the first row here. In this case, for example, if we have all the 4 sequences, then that means they are all of them are available, right? So what's happening here? Actually, that is our reference, right? So what's happening here? You can look at, for example, at the DICE index or a Hausdorff index. That's a reference that we would like to match, okay, or to be close to that, because we have the 4 sequences. Okay, then what about if we have an empty? That means, for example, if flare is missing, or T1 contrast is missing, or this T2 or a T1. What's happening to that results? If you look here, you can see that the most problem is using the T1 contrast enhanced or a flare. It drops the results into a very bad scores. But if you are missing a T1 or a T2, that means it's not a lot of drop. It's not like a significant drop here, which is okay. That's actually what's happening in our case when we are dealing with the Seoul National University Hospital. When they said they prefer to use T1 contrast enhanced and flare. So if something of these actually is missing, then actually it's a problem in terms of segmentation. So in our task, we are trying to synthesize this flare. We didn't touch this one, T1 contrast enhanced. And the problem here, by a Nature publication, and the reference in the paper actually, is T1 contrast acquisition. As I said, it is same as a T1, but we need an injection of a material into the body. So actually something gets changed. So we cannot actually using AI to synthesize that T1 contrast enhanced without injecting that material. Because of that, we assume that we cannot, based on that claim actually, we cannot synthesize this T1 enhanced. So we are focusing if only the flare is missing. So one other trial is, for example, if we copy, we said flare is somehow a T2, right? What if we copy that T2 to be a flare and do the segmentation? So you can see that there is an enhance from 68% to 80% in terms of the DICE. So now let's do the synthesis network, which is our network. So if we synthesize a network, as I said, using a T2, then we can get 87%, which is much closer to the original one, which is using the others. And of course, we do investigation using different combinations of using, for example, all the 3 levels sequences to generate that flare, but it didn't provide a much information just if we are using the T2. And that is why, because flare actually is a T2, but with a different pulse sequences. And here you can see that these 4 scenarios. If the flare is available, which is a ground truth, if we introduce a 0, which is in this part, is some problems happening, it's not a good segmentation. And if we just copy T2, you can see that other parts appear here. And here is our case using the synthesize from T2. Okay, now let me move to the other problems, which is if we have a noise labels or we have a limited number of data. And that's what's happening in medical domain. So one work actually is to solve these two problems is in our group. It's based on my student, Abdul Khaliq Al-Faqih. Now we are in the round number 3 at engineering applications of artificial intelligence. So with a minor, so hopefully we can get acceptance soon. And this study actually would like to address these two problems. And the main idea is to use a meta learning way. So let me introduce you the problem and what is the intuition about how can we address that. Here you can see that we have a problem actually in terms of fine annotation. So the segmentation labels, actually, the mask could be not even precise. That's bring us with a noisy problem. And another thing is sometimes the data is taking a lot of time, which means that we suffer of getting a lot of data sets, which is about the view data sets. So we can see that some clinicians these days start with some computer-generated labels. They can use AI models to generate the labels. Then they can fine-tune that, which still provides some problems. And when we look deeper in our maybe one of the data sets based on the Prats, we got one point here actually, which is about ground truth, which is a mistake by the annotators. But actually we treat that as a ground truth, so we cannot maybe change that or check after them, right? And sometimes is based on the interoperability between different clinicians. And that is the noisy label effect. And for the few data, for example, if we are talking about the adult brain tumor, which is glioma adult, we have over than 1,200 cases. But if you look into Africa data or pediatric data, they are here 99 cases and 140. That is the viewed data set. And here the two challenges I'm mentioning. The first one is if we have a single problem in maybe annotation, and as said, we provide a supervised learning paradigm. At the end, that could actually compromise the presence of that noisy, because when we train, we need to compute the loss function. Then that wrong labels could affect your training actually, right? So our idea here is we would like, if we can, to identify the clean data from the noisy labels. So if we can do that, then actually we can higher the weight during the training of those clean and lower the weight for those small data. And for the second problem, is same thing. For example, if we have we are treating with a pediatric, which is a small number of data, but we cannot train it alone. So if we would like to add more data from the adult, the network could be biased toward those of adult structure, not to the pediatric ones. So the main idea here again is if we can identify those of adult and small data, then we can higher the weights of the target ones, which in this case is a pediatric and an Africa cases. Okay, and of course lower the adult ones. This is basically the meta learning. So actually, this is not only the work that address this problem, and as maybe presented in literature, we can say that a fine-tuning a model that could start with a noisy data, then have a model, just fix some layers, and then retrain, fine-tune the model using a clean data here, okay? That is could be one solution to address the noisy data. But the main problem here, because we would like to train using a noisy, big number of noisy and big number of clean, right? At that time, actually, we need to do a further step in terms of categorizing the data into clean and a noisy data. And a similar thing happens here in a curriculum learning. So in terms of, we need actually still as a limitation is to separate and select which one is a noisy and which one is clean. So what's happening here, they do the opposite training paradigm. So they start actually with the clean, and they start gradually during the training add more noisy data in terms of add the complexity to the network. And so, as I said, the limitation was for these two methods is to separate those data manually. So in our case, for example, in a meta-learning paradigm, what's happening is we can just select a few number of data. In our case, we selected 10 samples only that we know exactly that they are very clean. There is no noise. So what's happening there? We can compute some gradients during a training, and we can have those a bunch of data that could be clean, that could be noisy, and then we can go do the same thing in terms of a gradient calculation. At the end, we would like to force the model just to adjust the weights of those of noisy ones to be lower, and those that highlighted and match the ones computed using the clean ones to be higher during the networks. And here another intuition about that. For example, here the green dots are for clean data, and the red ones are for the noisy data. So what's happening? What we would like to do using these clean ones, just to have some gradient information, then we can hire the weights for those green ones, which are for clean ones, and reduce the ones for the noisy ones. And a similar thing, if we treat them as a adult data and a pediatric, then we can increase the pediatric and reduce the adult weights. So then how we can get a noisy data actually? So we assume that the ones presented in a BRATS, the ground truth that they are available for us, they are clean. Then we do like 40% of these data to be noisy using some maybe morphological operation, erosion and dilation processes. So we can create more different data with the different scales. So if you look into the framework itself here for the meta learning, so we have a network, which is a sharing unit, for example, that could contain a pool of data that could contain a clean and a noisy. We don't know, okay? And the other one is the same network, but now we can train it on a meta cases, which we call it to be like a view and curated, selected, clean labels, okay? Only all of them are clean here. So what's happening here is we can get some gradient computation for both networks. And after that, we start adjust those weights. For example, we know, for example, now as for labels, we know that this is true and this is, for example, a noisy, okay? Of course, we don't know it during the training, but we'll know during the computation of the losses. So here per sample gradient, we have a different losses per each batch. And after that, we can get their gradient, right? Now we can do the same here for meta cases. Now, for example, we have a viewer data. So we would like to draw the cosine similarity actually. So we have a meta cases, which is here. We would like to compare all the gradient from all the data batches coming from the pool data sets. So if it is aligned as a cosine similarity, that could be considered as a clean data. If it is not, then it can be considered as a noisy data. After that, once we know during this operation, now we can actually refix, readjust, reweight the loss function. Okay. At the end, we can get a good maybe convergence during the training. Here, just a pseudo maybe an algorithm for that. So we have two loops. The one that compute the gradient for training data and for a meta data, we can compute the cosine similarity. Then after that, we can have like adjusting the weights of the network. If you look to the results, okay, I think I'm okay with the time, right? Okay, if we go to
Professor, we have about 10 minutes. At most 12 minutes, then the session is going to close. Let you know.
Okay, thank you. Okay, based on this, you can see that Here, for example, if we train the model using only the clean data, then we can have, this is our upper limit actually. And if we train the model using both clean and a noisy data, then you can get these average scores in terms of a dice coefficient. Okay, this is a upper limit, and this is a lower limit. And if you look into different models using curriculum learning or a meta cases networks, they get a good maybe a performance compared to the lower limit, but it's still far from the upper limit. But if you look to our proposed network, I explained, so it is almost there as a clean data, because we force those to follow the clean meta cases. And here we do some investigation about if we select how many cases we would like to select as a meta cases, which is a clean cases. For example, if you have a 0 clean and all the data, for example, 255 as a noisy, then you can see how the dice score gets reduced, right? It's below than 45%. But if you add only 10%, so you can see that more than 30% have been increased here, right? And you can see that once we include more and more data, that could be better and better. But the problem actually, as I said, we need to select those manually. Because of that, we assume that, okay, 10 cases could be a very good, in our case, having those, reducing that drop in terms of take caring of a noisy labels. Same thing happens for a data scarcity here. As I said, this is a glioma, which is a very big data we have. For the pediatric, we have only 99%. And there is another problem. If you have a look to the labels here, the necrosis part becomes actually, it was in the middle, in the center of the tumor. But here for the pediatric people, becomes in the outer part, but in the inner part is the enhancing ones. And this is for Africa, which suffer from the image quality. Maybe those people in Africa, they have a limited budget to get a good scanners, a good image resolutions. So what's happening in a data scarcity? We maybe, for example, if we can use only the adult, then the pediatric could be affected. What about if we can train the model using only pediatric, which is a very limited data? That could be not a very good option. What about if we mix both adult and pediatric that provide the maybe enhance the results, but is still suffering because the network gets biased toward the structure of the adult, not to the pediatric. So here is our case, which is a meta learning. We can use both of data, pediatric and adult, but with the focusing on the adult ones as a meta cases, then we can enhance the results. And that's what's happening here on that networks trained on a different populations. Using a pediatric only, we have a very bad results because it's very small data set. Using the Pratt's adult data, it's increased that. Mixed of these two, it's increased, but using our data with a fine tuning is increase the results better and a better. And here's some qualitative results. This is the case for Africa. Same thing, you can see same pattern happens here. Okay, and before maybe concluding the presentation, I would like also to provide you like a foundation model in terms of segmentation. An example for that is a MedSam. What is the meaning of that foundation model is, could we have a model that could do all the segmentation tasks for everywhere in our human body, including the brain tumor and the other things? Actually, that's what people, and which is the trend of these days. So what's happening, if you look here, number of data that in medical domain that have like images with the masks, MRI and a CT and endoscopy are the most three data sets that we have. So MedSam actually is one of these networks. It could provide you a segmentation for anywhere you would like, but the problem, they are like promote. So it is not fully automated. This is one limitation. So you need to provide some bounding box information. Then the MedSam can provide you that segmentation information. And you can see here different application and different segmentation results, which with a wonderful results. But another limitation besides that, the autonomous one, is the segmentation of these foundation models so far they don't care about some subcategories. For example, here, if you look, they can segment the brain tumor, but not the 3 levels of these brain subregions, which is edema, enhancing tumor, and necrosis, right? Because of that, actually, we are like in need of foundation model that can provide us all the such of the technology, and we are working on that actually. But the result is not completed yet. So let's recap what I'm telling here for this talk is I'm considering a different maybe challenges in a segmentation, particularly in MRI data. The first one was using a missing. If there is a missing data, then we handle that using a knowledge distillation or image synthesis. And the other one is when we have a noisy or a data scarcity, then we can solve that using a meta learning paradigm. Thank you very much for your attention.
Thank you so much, Professor. We really appreciate this great presentation. And I wish good luck with your, great work and with your team. And
thank you very much.
And you have a lot of, congratulations. And there are some questions, but only we do have 5 minutes, just that you know. And you can just write your questions to Dr. And also our co-chair, Dr. Mugayet El-Antari, is also in our list, and he's also listening us. And if he would like to say anything about our conference, his thoughts, this also welcome. And
yes, Professor Ahmed, thank you so much. We would like to express our gratitude to Professor Al-Masni. He presented very well. Thank you so much, Professor Masni.
Thank you, Professor Al-Antari.
Yeah, really, it is very amazing that if we can do work in the foundation segmentation models for medical AI, that's what we need to do. But exactly. I have one question here. For example, these foundation models can segment the subcategories, or it is still, a challenge for them?
If we are talking about like a general ones, like the ones I presented in the medical mid-SAM, I believe they are just providing a binary segmentation. So they cannot provide subtasks on that. But if we retrain, fine-tune those to be maybe handling our maybe specific tasks, I think that could work. But I believe we need I think this is still a gap, and we need a foundation model that can do anything, including the ones with the subgroups.
Yes. Okay, so in your opinion, Masni, how can we, tackle these mid-SAMs to target the multi-classes segmentation labels?
Okay, in our group, actually, we started working on this problem, and what we do is to make it a foundation model, but at a certain task. For example, for brain tumor segmentation, we have a different variability. Like we have a 5 cohort actually: adult, Africa, pediatric, meningioma, metastasis, right? So we need a foundation model only for those tasks, not for everyone, right? Not for the CT, the liver, the other organs. So I would like to specify the problem, shorten the umbrella a little bit, but still foundation on that task. So what we did is using like a multi-teacher models with a single student. So every teacher could learn specific cohort and then distill the knowledge to that student. At the end, student model have the information from all the cohorts, the 5 groups, then it could work. Okay. It works somehow well for some tasks, but it's still in terms of investigation how to make that like estimating the probabilities and other things.
Okay, thank you so much.
Right. Thank you so much, professors. Welcome. And we do have last 2 minutes, and for the question, if anyone would like to ask, we can get 2 more questions in the last 2 minutes.
I think welcome for any questions if you want.
Okay, 2 persons would like to ask questions. If they have any questions, please, they can ask. Okay. Thank you so much, Doctor. I really appreciate your effort, your diligence, and sharing great thoughts and great papers and future works. I believe this will be inspiring a lot of our, listeners for their work. And thank you so much again.
Thank you very much, and have a nice day.
Thanks.
Yes.